Hello. So the next chapter is about the sampling distribution. In the previous chapter, I explained that the normal distribution will be the only distribution we are going to use, and all the examples and all the distributions and all the random variables that we have in this course, in the remainder of the course, will be converging to the normal distribution. So this chapter we will study how a random variable converges to the normal distribution. So chapter 7 is actually very important. As I said, I will explain why we only need the normal distribution. So if you can understand this chapter, then it will simplify a lot of things because the only thing you need to know is the normal distribution. And also, this chapter is important because from now on, from this chapter, we can classify the content as statistical inference. So far, in the previous chapters, they were more theoretical. We consider some random variable in distributions, assumptions, and we studied their theoretical properties. But in fact, what we actually do is estimation, right? So we would like to estimate something. That's the ultimate goal of statistics. So at some point, we have to change our approach to statistics, and this is that bridge. This chapter will bridge between the theory and the actual inference methods. The idea is that the main difference between statistical inference and what we have learned so far is like this. So far, we considered only one random variable, like or two at most. So, like our approach was like this: when there is a parameter and when there is a set of assumptions, when they are given under these assumptions, under a certain value of parameter, then we studied how the random variable behaves. But in practice, we are going the other way. So in theory, we assume parameter and then we study the random variable, realization of the randomness. But in practice, what we observe is this realizations. That's data. We observe data, and from the data, we have to guess what was the underlying parameter that generated this realization. So to go the other way, to do the inference, we studied the other direction first, right? So after we understand how random variable is generated, then we can learn how to utilize the random variable observations, right? And another big difference here is that so far we considered only like one or two random variables. One or two random variables is of course easy to handle. That's the very basic theory. But in practice, we have data, which is usually huge. So usually we observe a lot of observations in practice, and that's the data. And then when we have multiple observations, then we may learn something new. That's another difference we are going to study in this chapter. So then let's start. And the sampling distribution is the keyword in this chapter. But by the way, relative to the textbook, I am spending more time on this chapter. I think this chapter is super important, and also it can be quite confusing, right? So, because as I said, we are going this way and then we will go the other way. So the first part of statistics is going like from parameter to data, but the second part of the statistics goes the other way, from the data to estimate the parameter. And this chapter is in the middle of them, in between them. So it's a little bit confusing to see what we are doing. So I particularly spend more time and I put it as a new chapter. I don't like most textbooks. Like maybe most of these textbooks may not have enough explanation and does not deliver the basic intuition and the purpose of why we are doing this. So I want you to like understand that and pay a little more attention to what I do here. So let's think about this simple example first. Suppose that, as before, I'm going to define a random variable x as a person's annual income, right? So you know how the randomness is coming from. You randomly choose a person. That's where the randomness is coming from. And when you randomly choose a person and ask her or his annual income, then you observe x. The answer is x. So then we write x follows normal distribution with mu and sigma squared. You know this notation, right? In this notation, what's random? It sounds quite obvious, but understanding what is random is quite important. So the question is like x is x random, mu random, sigma squared random, or is mu and sigma squared random, and all of the three. Guess what? The answer is A. The only random part in this notation is x, because that's what changes every time. So right, so you may understand it this way. This is a random experiment. You are doing, like, if you can do random experiments again and again, so you choose a first person and get his income, and let's repeat it. Like, if you choose another person, another random person, then you get another income. So each time the income, the actual observed income, is different, right? That's x. The income is x, and it takes different values if you repeat the same experiment. So right, that's one possible way, and like an intuitive way to understand and explain what is random. On the other hand, think about mu and sigma squared. Mu is the mean. It's mean income. So for example, if you think about mean income, then it's mean of everyone, mean average of everyone. So it does not depend on a certain person. If you like anyhow, I belong to that everyone. So no matter who you choose, they are just part of that everyone. So their mean does not change. It's just defined from everyone. Similarly, the variance is also the variance of everyone, or the measure of variability of everyone, right? Everyone's income. So, like when you define the mean and the variance, they are parameters, so they contain information of everyone, so they are common to everyone, and they don't change when you repeat an experiment. So if you choose the first person and when you choose the second person, the mean income is the same, right? No matter how many times you repeat, the mean is still the same mean, right? So in that sense, the parameters are not random, right? So, like obvious, so far it's obvious, but I will make it more confusing and more tricky. So, okay, now you see why x is random and why mu and sigma, the parameters, are not random. That's acceptable. And then I will say this. When an object is random, then we learned we can define the probability distribution. Yeah, obvious, right? Right. And also, when something is random, then you can calculate the mean and the variance if you know the probability distribution, right? So don't forget these two. I told you if there is something random, then we can define probability, mean, and variance. We are going to use this simple idea later, and then later, suddenly it doesn't sound right, but this is right. This is certainly right. Nothing to question, right? Then put it this way. Now let's change the situation a little more realistic. So in the previous example, I considered choosing one person. But as I said, in real real statistical practices, we are more like doing a survey, not just one person. Um, so consider a research center conducted a survey of 1,000 people. Now it's 1,000. That's the only difference. And 1,000 people's annual incomes are recorded. And then what they do is they calculate the average annual income from this survey of 1,000 people. And we are going to denote the calculated average income as X bar. So this notation is called X bar, and usually it stands for the average, calculated average. So in this case then, I will ask you this. Is X bar random or not? So the answer is random. It is random. The reason is because if you repeat this survey is where the randomness is coming from. You are choosing 1,000 random people. So if you repeat that, that means you choose another set of 1,000 people. And if it was random, then those 1,000 people would be different from the previous 1,000 people. So if you randomize repeat the experiment of surveying, then you will get a new set of 1,000 people, and of course, their incomes must be different, and then X bar must be different, right? So, like by the randomness in choosing 1,000 people, their incomes are random, and as a result, the average is random. Exactly same structure. When you repeat experiment, the value can change. Is that right? Then, obviously, X bar is random. Okay. Then, so this is what I explained. And here also, what I want you to think about here is, now we are going to consider choosing 1,000 people as just one experiment. That's the main difference. In previous chapters, we thought it as 1,000 repetitions of an experiment. That is not wrong. But what we need in statistical estimation is this approach. We have to think choosing 1,000 as just one experiment. That's the difference. We will, you have to understand that the difference between these two approaches. One is understanding like this as 1,000 repetitions of simple experiment versus like just one experiment of survey, one survey. So as I said, in the end, we are going to use this approach. Survey is just one experiment, but we are going to, like, of course, there must be relationship between these two approaches, and we will utilize that relationship in estimation. That's where this relationship is the sampling distribution. That's what we are studying in this chapter. Okay, so let me continue this in the next video. So, what I said can be confusing, but it will become more clear with more examples. So, I will continue in the next video and see you there. Bye.